Okay, so I'm supposed to lecture on cluster algebras to you. Actually, I don't remember picking this title, but maybe I did. But okay, anyway, I'm very happy with it. That's not a complaint. But I did have to kind of think a bit about what I was going to say, because it's such a broad topic that you could easily fill more than 3 lectures, and just on cluster algebras alone without any applications to physics. And since I'm a physicist, I probably ought to say something about the applications to physics. So I'm going to try and get to thinking about scattering amplitudes and various aspects of scattering amplitudes, and that cluster algebras can show up in various different contexts in scattering amplitudes, some of them not even particularly related to each other. And so the way I've kind of organized this to try and get there, so I'm going to try and aim towards getting towards the physics towards the end of the lectures. And I've put sort of something a bit more technical at the beginning. So today's lecture is probably going to be slightly technical, because otherwise I have to introduce what a cluster algebra is, and I have to introduce the basic machinery that goes with it. Although some of you I know are experts in this, so you will probably find this introductory part quite boring. And what I want to do is to in introducing that, I want to get to a particular piece of machinery which allows us to study automorphisms of cluster algebras. And that's going to be a useful tool, and then we're going to be able to explore that in the context of Grassmannian cluster algebras in particular, in order to understand some features of scattering amplitudes that show up at higher multiplicity and their potential, still conjectural, relations to scattering amplitude, to cluster algebras. Okay, so that's a very sort of rough outline of what we're doing. I mean, maybe it's just worth saying a little bit. So I mentioned scattering amplitudes at higher multiplicity, and what I have in mind is scattering amplitudes in planar n equals 4 super-Yang-Mills theory, which is, of course, a toy model, but it's a gauge theory in 4 dimensions, and so, at least in perturbation theory, it has some relevance to studying gauge theories in general, in particular QCD, which is obviously experimental relevance. And the way it shows up is in talking about the analytic structure of those scattering amplitudes and how the various, so we think about scattering amplitudes as analytic functions of kinematic variables, and as such functions, they have singularities of various different types. And we will see that the cluster algebras seem to tell us something about the poles and branch cuts that scattering amplitudes exhibit, and the relations between the two. These singularities sort of talk to each other in interesting ways that are dictated by the cluster algebra. Okay, so that's one aspect. There's other aspects which are closely related to tropical geometry. And a particular toy example in that case would be the bi-adjoint phi-cubed theory. The bi-adjoint phi-cubed theory at tree level has a very simple combinatorial structure, can be quite directly related to the tropical version of the Grassmannian GR2n. And so there have been speculations whether or not, call them alternative physical theories. Physical is maybe too strong, but some interesting amplitude-like generalizations of the bi-adjoint phi-cubed theory that are associated to higher dimension Grassmannians, GRKN, so-called CEGM amplitudes. Okay, so that's related to tropical geometry, and I guess also kind of part of what I want to describe at the beginning is introducing the parts of cluster algebras that are very directly related to tropical geometry. So we'll hopefully see these various connections show up. Okay, all right. Okay, so I am, having sort of given you a very wordy motivation, I'm going to become a bit more technical. I have to say something about cluster algebras. Let me introduce some notation. So let's see, we have some basic data that we use when we're describing cluster algebras. Okay, there's a semi-field that hangs around, and I'm not going to really use it very much, but in the kind of general formulation, we should think of our coefficients of our various variables taking values in some semi-field. So we'll call P the semi-field. Okay, so it has a multiplication operation, which is invertible. It's an abelian multiplication operation, and has an addition rule that's not invertible. You can add things, but you can't subtract things. Okay, so we have this thing, and we have some field of rational functions. So we call this F. Okay, and we're going to be playing around with lots and lots of rational functions. Okay, so they're going to be in some number of variables. We'll also have n variables. We'll call the variables x1 up to xn. And the coefficients in these rational functions take values in this semi-field. And then what we have is the idea of various guises of this field of rational functions showing up over and over again. So to do that, we imagine there's some tree structure. So draw some nodes with some edges, and each node has the same number of edges. In this case, I'm drawing 3 edges per node, but it could be n edges per node. Should be n edges per node. And then to each vertex in this tree, so we have a tree, n regular tree, and then to each vertex, we put some data. We call it a labeled seed, and use the notation sigma t. So the vertices here will be called t. There's a vertex t. To each vertex t, we put sigma t. So sigma t, what does it have in it? It has n of these rational functions in these variables. I'll call that xt, the vector of them. It has some coefficients, sit in p, n of those. And it has an exchange matrix, call it B, also labeled by T. Okay, and then to each edge in this tree, there's an operation. So if I have a node T and another node T prime, and that's edge K from this vertex to that vertex, then we have an operation that tells us how to get from one node to the other. So this is the mutation at node K of the seed at label T. Okay? And so now I have to tell you, what is this mutation operation? Okay, so this is this mutation. Takes us from one node to another. And so I need to tell you how to get the new data from the old data. So first I'll write some formulae, and then we'll think about some pictures. Okay, so this bracket operation, bracket something, anything, A sub plus means the maximum of 0 and A. Okay, so I've got some matrix of integers. That's this B matrix here. The coefficients are the BIKs. There's some integers. And then this mutation relation tells me that I should replace, if I mutate at node K, I replace the X variable on node K by this right-hand side where I evaluate some combination of product of all the X variables where BIK is positive, and then plus the sum over the X variables where BIK is negative, minus sign. Okay, and to the relevant power. And then I divide by the variable k. And I'm basically going to work with all the coefficients set to 1 in a minute, so we don't need to worry too much about the y stuff. But there is a set of variables that I do want to introduce. So, okay, I've given you a formula. I'm going to give a geometric, well, maybe I should do it straight away, in fact, given that we've got this. So let's think about this formula in terms of pictures. So this matrix B, it is going to be I said it's an integer matrix, but we're going to require it to be skew symmetrizable. Okay, so you can find some diagonal integer matrix, which will make you multiply it by and it will become skew symmetric. So we have this B matrix, it's called an exchange matrix. And we can think of it as being encoded, at least in the case where it's skew symmetric. Let's imagine that it's skew symmetric for now. We can think of it as being encoded by a quiver diagram. So if B is skew symmetric, then we can think of Bij as equal to the number of arrows in a quiver diagram from I to j minus the number of arrows going from j to I. And some very simple examples. So kind of the basic non-trivial example is the A2 with just a node, quiver with just 2 nodes, 1 and 2, and a single arrow that goes between them. And this encodes an exchange matrix, a single arrow. So I write element 1 from I to j, so from 1 to 2, 1 to 2, 1, and it's skew symmetric, so minus 1 arrow from 2 to 1. Okay, so I have this exchange matrix. Another example, the next one up, if you like, A3. This one actually becomes relevant for n equals 4 superunion Mill scattering. So the A3 example, I have 3 nodes, 1 to 2 to 3, and the exchange matrix would then be skew symmetric, 3 by 3. I have 1 here, and 1 here, minus 1, and 0. Okay, so we've got this pictorial representation. You can adapt it to the case that B is skew symmetrizable as well. Let me not bother. Okay. And then this mutation operation, so I wrote down what happens to the variables. I should also write down what happens to the other data. Okay, so there's a rule for the coefficients. Like that. Is if j equals k. If j is not equal to k, this. And then there's a rule for the exchange matrix. So when I do a mutation, the exchange matrix also changes. So if the element is either the kth row or the kth column, then you will flip the sign. And otherwise, you take it and then you add a term you can write in many different ways. But here's one way to write it. Okay. All right, so we'll come back to the variables in a minute. Let's look at the exchange matrix. So let's mutate on an exchange matrix. So what we can do is we can mutate here. We can pick a node to mutate on. That's going to be our node K that we do the mutation on. Let's do an example. Let's do this one, for example. So I'm going to mutate this guy on node 2. So if I'm thinking in terms of quiver diagrams, this rule is equivalent to the following. So, so for each pair of arrows that you have that go into node K from I and then out to J, so suppose you've got a pair of arrows that go in and out, then you add a new arrow from I to J. Then you reverse all arrows going into K, into or out of K. And then if you get them, you delete opposing pairs. If you end up with an arrow between two nodes and another arrow going in the opposite direction, you just cancel them out. Replace that with cancel an arrow. Okay, so in our example, if we do this, then on the quiver diagram, we've got one pair that comes in and goes out, right? 1 to 2, 2 to 3, that's our only pair. So mutation here give us a new diagram, 1, 2, 3. I add a new arrow from 1 to 3, and then I reverse all the other arrows that were there. Okay? And I get a new exchange matrix that looks like this, and then, well, we can read it off from the picture, still skew symmetric. There's an arrow from 1 to 3, there's an arrow into 1 from 2, and there's an arrow into 2 from 3. This would be your new exchange matrix. Okay, so there's a sort of formulaic way to do it and a pictorial way to encode the same operation. Notice your B matrix, it might have full rank. So this has full rank. Or it might not. This one does not. Okay, now there's another set of variables that I want to introduce that are very important for what we're going to do. And there's various notations for them. So up to now, I've followed Fomin-Zelevinsky's notation, who introduced the sort of introductory papers on cluster algebras. They call these new variables y hat, and it's a pain to write a hat everywhere when you're giving a Blackboard talk. So I'm going to call them z. And I'm also going to sometimes call them edge variables for a reason that we'll see in a minute. So I'm going to introduce these edge variables. So what is it? I'm going to take the coefficient and I'm going to multiply over the original variables x, take the product over all of them to the power bij for the jth edge variable. And I think of this as some rational function in f. This is some combination of the variables I've already got, some auxiliary data that I'm introducing. Okay. Okay, in some sense, the point of writing this out really was just to copy. So they have a very simple mutation rule that follows the y's. So if I want to mutate on node k, then if j equals k, this is meant to be the same. So if j equals k, you invert the variable simply. And otherwise, you take the variable and you multiply by this same object here, ekj plus. But now I'm doing everything in this field of rational functions. I'm just literally adding up, multiplying and adding in f these rational functions of our original variables x. Okay, so they have a sort of two things to distinguish. We're going to be interested partly in the x's, mostly in the z's. Yeah. The x's, you do nothing on a node unless you mutate it. So you leave all your other nodes alone and the x's don't change. And then if you mutate on that node, you just replace that x to get the new x in your new seed. The z's are kind of opposite. So the z's, if I'm mutating on a z on the node, then I keep the variable, albeit I invert it, whereas generically all the others change in some way. Okay, so in that way, you can sort of think of the z's, they kind of live on these edges, right? The z's are in every, if I have a z in this seed here, associated to this edge, it's still here, although it's inverted. I should write 1 over z, I guess. But it's associated to this edge in this tree diagram. Okay, all right. So if we start playing about with these things, we start generating, now you're going to love this, we start generating lots of data, and I saved myself the pain of writing them down in a Blackboard talk. So I have pre-prepared some data that you will generate if you do some mutations. You should have seen the example that I was going to do before this. All right, so, okay, so the example I took is like this one. So here, I took this example. We have node, we have this B matrix, 0, 1, minus 1, 0. We have variable x1 on node 1, variable x2 on node 2. And then, because we've only got 2 choices of nodes for each vertex in our tree, actually this tree is already too complicated. This tree is good for the A3 example, but the tree for the A2 example is just a line with an infinite sequence of dots. Right? I can mutate on one node or the other, and I should have said mutation's an involution. So if you mutate on the same node twice, you come back to where you were. So our tree, I haven't really, okay. So our tree is a sequence of nodes that look like this. And here I've written out 6 nodes, T0 to T5. I started on T0 and I started mutating. So I called the variables on T0, x1, x2, and then I just followed this rule, and you can put the y's to 1. So ignore the y's for now. You generate the following set of rational functions in x. Okay, so we can just quickly check this one. So if I mutate on node 1, what do I have to do? I have to divide by x1, and then in the numerator, I have the product of have x2 to the b21. The b21's negative, so I don't. I just have 1. And then here I have x2 to the minus b21, which is now positive, so I keep it. So I just have x2 to the 1. So you can see you have to sort of think a little bit in order to piece together the various contributions to each term. As you mutate, you can see they can become slightly complicated. Of course, it's trivial to automatize. So that's a useful point for generating these things. And then you notice something maybe slightly surprising happens. Doesn't always happen, but it does happen in this example. I mutate, I generate some rational functions of the original variables, some slightly more complicated rational functions of the original variable. Notice the feature that I mutated on node 1, so x2 didn't change. We kept x2. Here I mutate on node 2, so this variable didn't change. I keep it, and so on. And then somehow they simplify again by some factorization. And then after I get to node T5, after I've done 5 of these mutation steps, I find I got back to x2 and x1. The B matrix, well, the quiver, I just drew the quiver. The quiver is flipped around the other way. So I've got the negative of the B matrix I started with, and the variables are on opposite nodes. But that's the same up to permutation. I can just relabel my nodes 1 to 2 and swap the labels. And I actually have the same diagram that I started with here. So this thing, when you iterate this operation, which I just introduced, either with the formula or the arrows, you go around in a closed cycle after 5 steps. Okay, it doesn't always happen, and that depends on precisely what kind of B matrix that you give yourself to start with as to whether or not that happens. Okay, so I also did, and these are going to be useful for us, the equivalent operation doing the Z variable, these edge variable mutations. So again, we start with Z1 and Z2. Now I mutate on Z1, so I keep it, but I invert it. But Z2 changes, and I get a rational function of my original Zs by doing this. Then I mutate on node 2, it inverts, and this one changes, and I get another rational function. But the same feature happens, that it simplifies in the same way, such that when I get back down to here, the data has just swapped sites. Okay, so we can say that so I called it, what did I call it? I called it a labeled seed. So the labeling just means which node is number 1, which node is number 2. We can say that the label seed on T0 and the label seed on T5 are equivalent up to permutation of the labels. There's an equivalence relation that you can just do by permuting the labels. Okay. I'm going to record these for later. We'll use these. Okay, let's see. Okay, so you keep that. And I can put that back up. Eraser. Yes. Yes. So these examples I gave you were skew symmetric, but skew symmetrizable means you need a diagonal matrix of fixed sign integers, but if you left multiply it into the B matrix, it will become skew symmetric. That's a condition on the definition of B. Yeah, absolutely. Yeah. Obviously, if it's skew symmetric already, you don't need to do anything. Okay. All right. So all of the cases that I'm really going to be interested in are what are called geometric type. And this coefficient semifield is about to go away. So we define this coefficient semifield, the so-called tropical semifield. It has some generators, U1 up to UR, say. And then we're going to explicitly define this semifield addition operation. So if I have, these are abelian. So if I have a product of generators, uj to the aj, and I semifield add this to a product of uj to the bj, then this is just a product of uj to the minimum of aj, bj. Okay, so now we've just got a bunch of abelian generators, and we've got an explicitly defined semifield addition law. And moreover, actually, things simplify. So we can denote our generators. Let's denote our generators. As xn plus 1. We had x1 up to xn already, so we introduced some more x's for these generators up to some xm, an r of them, and you can call them frozen variables. Then our coefficients yj, you can think of them as being given by some product from n plus 1 up to m, so over the frozens, some new set of numbers, bij, that augment the bij's that I already had, where the indices run from 1 to n, and now I introduce a bunch of new rows at the bottom of the b that we already had. And that's just explicitly writing out our coefficients in terms of these new variables, and they obey this semifield addition rule. And then, okay, things become very convenient. The mutation rule just becomes what you would think it would become. Write it. So mutation basically says, you can think of it as you've got no coefficients, you've got a bunch of variables where you do allow yourself to mutate, the so-called active variables from 1 to n, and another bunch of variables with some extended B matrix denoting how they interact with these ones, and we just never mutate on them. We just force ourselves not to mutate them. So they're in every seed. Okay, and then this extended B matrix, so we've got these extra B's here. We just have an extended B matrix, which was our original B matrix, and this bit that goes down here, the extra part. And the formula for the mutation of that is literally the same as the one that we wrote. Okay, so if we were doing quivers, we've just got extra nodes with arrows that can come in and out of the active nodes, but we don't mutate on them. This is this, under choosing our coefficients to be given by some frozen variables with some powers, extra powers bij that I introduce, and then this addition law is how you're meant to treat the semi-field addition rule here. So it just simplifies to having a bunch of variables x, some B matrix, which you still have to define to say what cluster algebra you're talking about, and then a set of active nodes where you allow yourself to mutate, and a set of frozen nodes where you don't allow yourself to mutate. Okay. Now, in some sense, the kind of reason I went through that is to introduce. Oh, sorry, yeah, go ahead. So UZ, so they will, right, so the frozen variables will enter. So what will happen is, having written our coefficients explicitly, all I will have to do here is extend this product over the new labels. So the frozens can enter into Z. But there are no Z's for the frozen nodes. Correct. Yeah, exactly. You just have them on the active nodes. Okay. Okay, so, all right, so there are various choices that you can make for frozen variables. If you've given some set of active variables, some exchange matrix, you can introduce different choices of frozen variables. And so there's one choice, which depends on the vertex. So you pick a vertex. Let's suppose we pick at vertex T0. We're thinking about the labeled seed at T0. And we introduce principal coefficients. So we're going to let our seed data be x1 up to xn, and our coefficients y1 up to yn, and our exchange matrix B. That's our labeled seed data. And then we imagine this tropical semifield, we just pick the y's themselves to be the generators. So if we do this, then we're going to have some all of these. So our coefficient are the generators. So we just have an identity matrix here. Just tells us this variable is that variable with power 1. So our extended B matrix, B tilde, is just our original B matrix with, okay, so I'm going to call it, called it here B extra, but I'm going to call it C in this case. Okay, so for a given node T, we're going to have this extra bit of B matrix at the bottom. It's also going to be n by n. And I'm going to call it C because it's like related to the coefficient. We'll call it a coefficient matrix. Okay, but it's really just like this extended B matrix. And we start off at the node T0, as we just said for node T0, these are the variables, these are the frozen variables. So this thing is going to be the identity matrix, this C at node T0, 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 It's just the n by n identity matrix. Okay. These are useful because, well, they allow you to introduce an extra piece of data, and the extra piece of data that I want to get to is called the g-vector, and that's the thing that we're going to study in a minute. So let's imagine we do our mutation operations. We're in this cluster algebra. We've put principal coefficients at our starting vertex. We can think of these YNs as like frozen variables. There's one for each vertex that comes in, and we've got, if we're drawing a quiver diagram, we can just imagine an arrow coming in from each coefficient Y to each vertex, 1 up to n. Okay, and then we do our mutations. And obviously, if you pick some cluster variable in some seed, it will be given by some explicit rational function. Okay, that depends on, well, the exchange matrix that you started off with. Okay, and since this definition of our choice of coefficients depended on picking a seed T0 for where we're going to put this identity matrix in the coefficient, and everything that I'm writing now depends on that choice of starting seed. And then what do you get? You get an explicit, okay, so in fact, you find this thing is expandable integer coefficients generated by variables, their inverses, and the coefficients themselves. Okay, so it's you only ever find in the denominators monomials of these x variables if you do these mutations. This is called the Laurent phenomenon. And moreover, if you set the x's to 1, you get a polynomial. So you can define a polynomial. You take your rational function that you got by mutation, and you just set it for a given cluster variable in a given seed, T, and you just set all the x's to 1. Get this polynomial. And what's slightly surprising is that this polynomial basically encodes everything about the cluster variables you want in any cluster algebra with any choice of coefficients. So you find that the cluster variable is given by some monomial in your original starting variables, in your original seed, some powers, g1 up to gn, times this f polynomial evaluated on the edge variables, z1 up to zn, divided by the f polynomial evaluated on the coefficients. So if you know f, you can reconstruct your cluster variable up to this extra piece of data, g1 up to gn. And this piece of data is called the g-vector. Just call it g1 up to gn. And note that it depends on some things. So what does it depend on? It depends on the cluster variable that it's meant to be representing. So there's one of these g's for each cluster variable. And it also depends on the choice of T0 where I started everything. So everything that I wrote from here on depended on this choice of T0. So these vectors depend on two things. They depend on the choice of initial starting seed, where you're going to record all your data. And then given that, there's one G for each cluster variable that you can generate as you do all your mutations. Okay, so in some sense, these Gs stand in for the cluster variables themselves. So we can study the cluster algebra by studying the Gs. Now, instead of worrying about lots of complicated rational functions, we can just think about these integer vectors recording information about we would get for each seed as we do our mutation. Sorry? Couldn't hear the question, sir. Yes. Okay, so it is related to, okay, so we're going to make a connection to tropical geometry through these G vectors. They do obey, well, I'm going to write a mutation rule, and it's related to a kind of tropicalization of the original mutation rule. Okay, so okay, so G vectors. Okay. So suppose you have a seed. It's got an exchange matrix with these entries that we've been using, Bij. And suppose we've got a coefficient matrix at that vertex, T0, for the seed. We're going to have entries Cij, T, and they depend on the choice of T0 as well. And the mutation rule for the Gs so again, like the cluster variable, having fixed T0, there's one for each x. So in the same way as the x is when you mutate, you just change that x for a seed and you keep all the other x's the same. Now for the G vectors associated to the seed, if you mutate at node k, you just change the kth G vector and you leave all the others the same. Okay, so then I just need to write the rule for how you change the kth G vector. Okay, so the rule involves not only the active part of the exchange matrix, but also the extra bit, the C's. And in this term, it remembers the exchange matrix that we had at our initial vertex T0. So this is the jth column of B at T0 that enters into this mutation formula. Yes? Yes, it is a consequence of what I've written, yes. Okay. Okay. Okay, so I've written out the rule, and it's sort of cumbersome, but you can, again, obviously implement it directly on a computer. And of course, on the second half of that board up there, I've done some of this mutation data in preparation already, so we can see the kinds of things that we get. Let me have a look at this again. So the way I encoded it, was, here's the C matrix. So again, we start off at T0, and the C matrix is just the identity matrix. That's what we said. We just put in the identity, the bottom half of the extended P. And then you follow your mutation rule as you go down, and this is what you generate when you do so, just following the same rule for the Bs. And then the G vectors are encoded as columns of this matrix. So the columns here correspond to the cluster variables associated to each node. Okay, so we ascribe, for the nodes, nodes in the original seed where we started with, we obviously just have those variables. So we have the unit vectors for the g's. These things go to 1. The g vectors in the initial seed are the unit vectors. I've unit vectored for node 1, unit vector for node 2. And then this is what you get by following this mutation rule that we have over here. And again, everything cycles round, and once again, you get to, as it should be, that the g vectors only depend on the cluster variable that you got, having chosen which node you're going to start with. So having here recovered x2 down here, I'd better recover 0, 1 down here, because that was the vector that was associated to variable x2. And likewise 1, 0 here. Okay, so if you do this, you get a set of vectors, and you get 5 such vectors that are distinct columns of these matrices as you go around, because there were 5 different cluster variables that you could generate here, 5 distinct rational functions of our x's. And then down at the bottom, I plotted what these vectors look like on a plane. Okay, so here's region 0 with the vectors 1, 0 and 0, 1 bounding it. So you get a cone in the plane. Cuts out this cone with the unit vectors. And then for T1, I keep the vector 0, 1, but I also obtain the vector minus 1, 1. And I get another cone here, labeled by T1, T2, T3, T4, and then I cycle back round to the cone that I had, albeit the labels swapped over. Okay, so this kind of fan structure is very useful for studying the behavior of the cluster algebra in general, and it's also very directly related to the tropicalization of the Grassmannian. So won't discuss that yet, but hopefully there will be time to discuss the tropical Grassmannian and how it relates to these G-vector fans. Well, I should say a part of the tropical Grassmannian, because all of this is related to the preservation of some positivity structure. Okay. Now, I could have done something different. I could have decided to start at node 1, if I'd wanted, and decided that that was going to be the node where I was going to put my principal coefficients. So I was going to write down the unit matrix for my coefficient matrix on node 1. I was going to use those basic variables to describe the variables. So these were going to be the unit vectors for the G vectors for that, would be the G vectors for that node. And then I would do the mutation, and I would generate a different set of vectors as I go around. And now they're labeled by not only the node they're in, but also the node that I started with, which is this T1. Okay, so you record a different set of data. And if I collect all the different vectors, so I've still got my unit vectors for where I started off in T1. And now as I go around that way. And then I come back, I go around that way, and I come back to where I started. And it's a different fan from the one that I started off with. Okay, and so there's some rule which takes me from one fan to the other. And this rule is a piecewise linear map. And in some sense, by definition, it does what it does there. It's piecewise linear within each of these cones, and it maps a given cone with the same label to the same label. Sort of tautologically defining what it does. More generally, you can write what it does. So there's a rule If I imagine that T1, I got T1 from T0 by doing a mutation operation. So we would like the rule that tells us how to acquire these vectors from those vectors by mutating the choice of our initial seed. It's different from this rule here, which told me with a given fixed choice of initial seed, how to obtain the G vector for the mutated node we fixed. Okay, so if G given by some vector, G1 to Gn, and now I want to obtain the same for the same variable x, but with respect to a different choice of initial seed, T prime, related by a mutation to T. Then you get this new G following way. So if J equals K, you flip the sign of the component. Otherwise, you add some amount of GK and you subtract some amount from the exchange matrix. And there's this piecewise linear minimum function that appears in the exchange relation for the exchange of the choice of seed. So with sort of the G vectors, we've got two pieces of data, the variable and the seed, which we are taking with respect to, and we've got a mutation rule for both. All right. Okay, and so there's some history to these relations.
Where does it
So, so yes, sorry, so where does it come from? Very good. So I'm mutating the initial seed, T0. Did I call it T0? I called it T now, sorry. So T, I've got, I'm changing this node T on node K to T prime. So I get the T prime by one step from T on node K. Thank you. Okay, so, right. So all of this stuff that I'm describing comes from Fomin-Zelevinski. This was a conjecture, I think, of Fomin-Zelevinski, but it was then later proved in some sequence of papers, which, okay, so I've written the authors in the notes. There's Derksen, Weyman, Zelevinski, and Plamondon, who dealt with the skew-symmetric case. And then there was Gross-Hackenkiel-Kontsevich, who dealt with the skew-symmetrizable case. And the formula, the direct proof that this implies this conjecture from Zelevinski, I think was in a paper of Nathan Reading from 2020. There's some sort of long history of things that were conjectural, I think, in Fomin-Zelevinski, but I believe what I'm writing down now is actually proven. Okay, so we're just going to take this and we're going to make use of it. So this is going to be useful for us. In particular, it's going to be related to our Z variables we introduced at the beginning. Now, let's see. Okay, so just something to note, which is useful. How much time do I have left? Okay, good. So suppose we have some cluster pattern or pattern of seeds associated to T, this tree. There are 3 others that are naturally related. So you can do all of the same operations, just flipping the sign of the exchange matrix. Okay, so we flip B to B opposite, we'll call it, which is just minus B. Okay, and for example, in the quiver diagrams, everything will follow through. All of the diagrams will look the same, just all the arrows will point in the opposite direction. Then there's the dual, is if I take the negative of B transpose. So if B is skew symmetric, then that's just B again. So we don't have anything. But if B is skew symmetrizable, we get something new by taking the dual. And then obviously having taken the dual, you can take its opposite. So if you take any of these 3 other things, the same pattern will work. You can follow through the combinatorics associated to exactly the same set of mutation diagrams. And in every seed, this will be the rule for converting from one B to the other B. Okay. All right. So in particular, it means, for example, you have each of these will have their own sets of G vectors associated to a given variable at a given node with a given choice of initial node. Okay. Right. Okay. So since this is here, let me make complete this sentence. So let me make a definition. So I'm going to introduce another version of another version of tropicalization. That's similar to what we said before, but there's a different explicit definition. So I'm going to take the tropicalization of a rational function. So suppose I have a rational function, and I'm interested, it's going to be a function of the z's. But that doesn't matter for the definition of what I mean by tropicalization. So it's going to be some polynomial over some other polynomial. And then we're going to define the tropicalization of the polynomial of this rational function. Well, first of all, it's going to be the tropicalization of the numerator minus the tropicalization of the denominator. And then for the tropicalization of a polynomial, that is going to be take addition and replace it with the maximum operation, and take multiplication and replace it with addition. Okay, so given a polynomial, you can make a tropical polynomial. So for example, and I've written trop plus because trop plus is going to be associated with the fact that I chose max here. I could have written trop minus, and that would have meant tropicalized with minimum convention instead. And actually we use both. Okay, so if I do trop plus of this polynomial, 1 plus z1 squared plus 2z1 z2, this is equal to 3 terms with addition. So it's a maximum of 3 arguments. 1 gives me 0. Z1 squared gives me 2. I'm going to call the new variable V. Okay, the tropical version of Z1 will be V. And then here I lose the coefficient, and then I'll have V1 plus V2. I replace the product with addition. Okay, so you get a piecewise linear function from each rational function that you tropicalize. And if I'd put minus here, minus would have just been do min instead. So this is not, okay, it's not a logarithm, but yeah, it's a bit like a logarithm, and I guess it's in the way it splits the multiplication into addition. But no, you lose this data. You lose this data in tropicalizing. Okay. So now the observation is that rule for the change in the G vectors is essentially the same thing as the mutation rule that we wrote down at the very beginning for the way the Z's mutate, but tropicalized. Okay, so let's see. So we do it over here. Right. Okay, so all right, so we're going to actually deal with the general case. So I'm going to make use of the dual. So let's imagine doing the Z mutation, but for the dual version of the cluster algebra that we started off with. So we'll consider the Z's in the dual and how they mutate. And we wrote down that rule before. So I'll call the variable Z dual, or maybe I'll call it Z check. Maybe that helps to compactify it slightly. So here was the mutation rule. This is me just recovering what we wrote before. Yeah, exactly, with the B negative B transpose. Dual B. I didn't do anything here. That was just me writing out what we wrote down before and putting hats on things, right? Because we're now in the dual. Okay, now what I want to do is tropicalize this. So tropicalize the right-hand side. So in the tropical version, okay, I'll call the associated variable B check, and maybe because it's a check. So what do I get? So I invert, that just becomes the negative. Okay, because the denominator comes with a minus sign, and then tropical of just a monomial is single power of the variable is itself. And then here, okay, so what have I done? I've just kept the product. I expanded out over addition. So I have this becomes this, times up here becomes plus. Then I get the power comes down, the variable, and then this factor, well, I have the negative power, so I get the minus sign, bkj is the exponent, and then the max over these two terms, which is this one and 0. Right? And then, okay. Almost there. A sort of slight rewriting. I'll leave that one alone. This one is, so now I use the fact that B dual is negative B transpose. And then I have to shift some contributions from one term to the other. And then in doing so, I end up with a minimum. But, so you can check, this formula really is literally the same as this by shifting things in and out of the maximum and taking signs. So when you have maximum of two negatives, it's obviously related to the minimum of the things without. All right, and now this formula is literally the same as this formula. Okay, so the upshot of it is, if we want to study the G vectors and we want to study how they transform under mutations, we just think about the edge variables. In principle, we should go to the dual, and we should think about how the tropicalization of how they transform. All right. And if I had done everything, so I did everything here with taking trop plus. But if I had done trop minus, what I would have got would be the change the rule for the opposite of G vectors. So how the opposite G vector, the G vectors in the opposite algebra would change. So I take the same transformation rule and tropicalize with trop minus, and you'd get the transformation rule for the G's in the algebra with the negative B matrix. Right. So let me very quickly, I've got 2 minutes, and then we will get to the point of what we wanted to say with these. So, okay, so well, it depends what you want to do. So if you want to study how the G, so the claim is if you want to study the G vectors in some algebra with some defined G matrix, then you tropicalize the dual with max convention on the edge variables of the dual with max convention. And that will give you how the G vectors transform. If you want the G opposites, therefore, you take the Z variables in the opposite algebra, the dual of the opposite algebra, and you tropicalize with max convention, but it's the same thing as tropicalizing these ones with min convention. Yeah. So you could, either way around you want to write it, but there's one rule. Okay. Right, so now we define a piece of notation that just does this for us. So it is defined to be a piecewise linear map. What is it? It's the piecewise linear map that I get by doing this. I get, it takes me from the G vectors with respect to node T, and gives me back the G vectors with respect to node T prime. And it's just this explicitly defined piecewise linear map, defined by taking the V's in the dual and mapping them to primed versions following this rule. Q is, yeah, plus for the max convention. So this Q acts on the G's. So the point is,
T is a T prime.
Yes, so we oscillated, but our convention was that it takes you from t to t prime this way round. So in other words, that the q plus t prime t on g vector for variable x with respect to initial node t is equal to the g vector for that same variable with initial node t prime. Just an explicitly defined piecewise linear map. And the same for the minus. So if I had done the minus, I would have put min convention. Let me not write it, but it would have, if I had done it, q minus t prime t would take the g vectors for the opposite and do exactly the same. Okay. And they compose, so obviously it's just a change of coordinates. So if I change coordinates twice, I've just changed coordinates. So if I go to t double prime from t prime, having first gone from t to t prime, then we can think of this as given by the tropicalizing the change of coordinates from the z's at node t double prime in terms of the variables at node t, which is just some rational function. Okay. Right. So let me say why we did this. So what we wanted to understand, having prepared everything in terms of mutations, are automorphisms of the cluster algebra. And one way to think of the automorphisms of cluster algebra, think about a quiver diagram, say, which describes the shape of the cluster and the entries of the B matrix. You could do a sequence of mutations that takes you through some set of other quivers, and then you end up in another final quiver with exactly the same shape as the original one. Okay, so it's got the relative arrows are all the same, but maybe up to a swapping of the labeling of the nodes on each, the labels on each node, but the shape is the same. But if you can do that, then you can generate via these means some sequence of these piecewise linear maps, and you can understand how the G vectors will transform under the automorphisms of your cluster algebra. Okay, so I've got I will stop now, but the next lecture we can do a couple of examples. We can go back to our toy example and study how the G vectors transform under a very simple kind of cyclic rotation as you go through the 5 nodes. But the main example that we're interested in is the case of Grassmannians. And Chris Fraser studied automorphisms of Grassmannian cluster algebras, and he found some interesting action of the braid group on the cluster algebra. And so we want to study the action of these braid generators on the G vectors of Grassmannian cluster algebras and try and learn something about the structure of the cluster algebra. And coming back to physics, we will see that if we understand something about those automorphisms, we will be able to say something about non-rational singularities, algebraic singularities that show up in scattering amplitudes at higher multiplicity for n equals 4 superangles. So we'll get to that hopefully in the next lecture to understand how all those pieces fit together. Yes, so I kind of need to apologize. This lecture was extremely technical, but I had to introduce a whole bunch of things in order to anything else to make sense. So hopefully it will partially digest, but feel free to come and grab me and ask questions if none of it made sense.